Alright, today we are going to look at a simple series parallel circuit. I've already done all the work and done the calculations, but the plan for today is we are going to fill in the measured value column here by hooking up the circuit, which is right here, through our leads to our power supply, which is right here, and we will use the Fluke voltmeter to make some measurements. Does it sound like fun?
Yes, it does.
Alright, so we're going to start out by looking at the circuit in a little more detail. And you can see that right now what I have is I have the 1K resistor here. I have, yes, the 1K, then I have a 5.6K and a 3.9K in parallel together. And then both of those go through a 1 ohm resistor, which we're going to use to measure the current. Remember we talked about that?
Yes.
Then back to the negative supply, back up here to negative. So
Correct.
Plus down through the circuit and back through negative, back up to the supply.
Correct.
Okay, so let's go ahead and turn on the supply here. That's a two-step process actually. We push the little green button and that initializes it and tells us we're going to have a 12 volt output. At a maximum it said 1 amp. Now it goes to 0 because the power supply isn't actually on. At this point we would be able to adjust the voltage if we needed to. We could set the voltage, but at this point we want 12 volts, so we're just going to go ahead and turn it on. And when we do so, it says that we have indeed 12 volts, and the meter's telling us we are drawing about 4 milliamps from the source.
I see that.
Okay, so at this point we should have voltages across our resistors, and we should have current flowing through them. So let's go ahead and set this on DC volts. I have to turn it off first and then turn it back on. Set that on DC volts. Let's find our probes right here, and I'm going to go ahead and give these to you, and we're going to measure the voltage across the 1K ohm resistor, which is the first one in the chart. And you got what, 3.677?
Yes.
Okay. If we look at the chart, it says here that we should have gotten 3.64, and we got what, 3.67?
Yes.
Okay. Let's go on then to either one of those. Since they're in parallel, they should have the same voltage across them. So if we measure the voltage across one, we should get the voltage across both.
8.31.
Okay, wait a minute. Do that again, please, just for a second. Now you did it the other way.
Yes, I did.
Okay, you had the probes backwards.
Yeah.
The number should be the same.
8.31.
And let's check the voltage of the resistor right next to it, which is that one.
8.31.
Okay, and since they have the same, they're in parallel with each other, as you can see, they both have the same voltage across them, so we can write down, what, 8.31?
8.31.
We calculated 8.36, but we have 8.31 volts across both of those components. Now let's measure the source just to make sure. We really don't have to because it's measured up here, but just to make sure, let's measure it across the circuit from here to there and make sure that we actually have 12 volts.
12 volts.
So we have perfect, right on, dead nuts, perfect. So we'll put that down for our measure. Okay, why is there a discrepancy, even though it's small? Why is there a discrepancy between the 3.64 volts that we calculated and the 3.67 volts that we measured, or 8.31 versus 8.36?
It would probably have to do with the tolerances of the resistors.
Sure, the tolerance of the resistors, any resistance in the meter that you might have. It's not a perfect world. We look at the nominal values based on the stripes that are on the resistors. That's what we use to calculate our values. Now let's go ahead and measure some currents. Okay?
Change this.
No, we do not. We don't change anything on the meter. I've told you guys before, we do not ever measure current using the meter as a current meter. We always measure current using the meter as a millivolt meter and putting a 1 ohm resistor in the circuit. Remember that discussion?
Yes.
Okay, I have a 1 ohm resistor in the circuit right now. So let's go ahead and review what our numbers are. It says that we should have a source current or total current of 3.64 milliamps. We should have a current through R1, and if we look at the circuit, clearly all of the current from the source has to go through R1. So R1's current is the same as the source current, or it should be about 3.64 milliamps. Then we should have 2.14 and 1.49, and these calculations were all done using Ohm's law. They're all right here, so you can look at those at any time. But we're here to actually do the measurements, and we're going to do our measurements by putting the current through a 1 ohm resistor. So what we have right now, if you look at the circuit, is we have a 1 ohm resistor here on the tail end of our circuit, but just before it goes back into the negative.
All right.
So what we have on our schematic is we have a 1 ohm resistor right there.
Mm-hmm.
Okay? If we measure the voltage across a 1 ohm resistor, V is equal to I times R. If R is equal to 1, then V is equal to I. So whatever we measure as a voltage across that resistor is what's going to be the current flowing through it. And since we're expecting a current in the milliamp range, we'll set our meter to the millivolt range so that we can measure the voltage. And it's already on the we're on the volt range. So let's set it to the millivolt range. Okay? Are you ready?
Yep.
Now let's measure the voltage across the 1 ohm resistor.
3.6. I don't know. It's
Oops,
moving.
you lost it. Yeah, I just lost the connection somehow.
3.6 millivolts.
Okay. 3.6 millivolts. Remember, voltage is equal to current because we have a resistance of 1. So 3.64 millivolts is equal to here what? What was it? 6.1?
6. It didn't come up with a less.
3.6 milliamps.
Right.
Okay, so we measured 3.6 millivolts, but being that that voltage is across a 1 ohm resistor, that means we have 3.6 milliamps, right?
Correct.
That's the same as the current through R1. Now, to measure the current through R2, here's what we're going to do. We're going to take our 1 ohm resistor out. We're going to put our connection at this point right there, and now we're back to the original circuit, right? Oops,
yes.
We're losing focus there. Now we're back to the original circuit. So if we want to measure the current through here, and I'm going to go ahead and turn off the voltage for a minute.
You have to take a leg out.
I can take a leg out and just move it to another hole, and I doubt you can see that on the video, but I move it to a different hole and then use my 1 ohm resistor here to bring it back over to the negative terminal. You see what's happened?
Yes.
We have a path to the negative terminal from here for this resistor, and we have a path to the negative terminal through the 1 ohm resistor here.
Yes.
So if I measure the voltage across that 1 ohm resistor, we'll turn the power back on right here. Boom, back up to 12 volts. Still drawing the same current, so we know I have the circuit probably hooked up the same way. Go ahead and measure the voltage across the 1 ohm resistor. You might have to press it down good to get a...
2.1 millivolt.
Okay, so that means we have
2.1 milliamp.
2.1 milliamps, and that's compared to 2.14, so it looks like we're pretty close, right?
Yes.
We have one more to do. Okay? The easiest way to do this, turn the power off again, is to simply swap out the two resistors. Is there any reason we can't just swap these out?
No.
Put this resistor here down through the 1 ohm, and then put the 3.9, whatever that was, 3.9K, where the 5.6K was before. All right? And we'll turn the power back on. 12 volts, same current. And now let's measure the voltage across the 1 ohm resistor once again. You're not getting a good tight.
Okay, it's reversed for some reason.
Not getting a solid reading?
No. Okay, that's all on the same. That's all on the same.
Well, the circuit has to be working right, though, because we're getting the 4 milliamps from the source.
Yep. 1.5.
There you go. Must have just been a bad connection or something. Okay, 1.5. Compares to 1.49.
Yep.
2.1 compares to 2.14. 3.6 compares to 3.64. Everybody up the whole ladder compares between the measured and the nominal or printed version. Okay?
Yep.
So do you see what we did?
Yep.
Can you do it yourself?
Yep.
All right. There, right over there is a circuit board and a set of resistors for you to build your own circuit. Let me know when you're ready to have it checked off.
Okie dokie.